Okay, so I wanted to say one more thing about substituted cyclohexanes. A values describe the equilibrium constant, well, describe the difference in free energy between having a group axial versus equatorial. And you can use it as a measure for how big a group is within some reason. So, as an example, methyl has a value of 1.7. That means the equatorial conformation is 1.7 kcals per mole more stable than the axial conformation. Notice when you add another group beyond the methyl group, when you tack on an additional CH3 to make it ethyl, that doesn't increase the A value much. It does increase the size of the group, but remember, methyl groups can rotate, and so it's easy to get that additional methyl group out of the way, and so the ring doesn't care so much whether it's methyl or ethyl. You start to introduce branching with this isopropyl group and it gets worse, and then another branch group and it gets even worse. And the differences here are all about the group you've attached to the ring being able to rotate to get whatever's here out of the way. Another factor that you have to be aware of is bond length, because that can sometimes lead to counterintuitive effects. For example, in terms of atomic radius, iodide is much bigger than bromide, which is bigger than chloride, but the A values don't change a lot. In fact, they may go down a little bit, and this is because carbon iodide bonds are longer than carbon bromide bonds that are longer from carbon chloride bonds. So, even though it's bigger, that's compensated for by the fact that the group is held further away. Remember that the thing you're trying to avoid in an axial conformation are these diaxial interactions. They're sometimes called 1,3 diaxial interactions, and they are worse if the bonds are shorter here. If this group is out further, there's not as much steric clashing. Lastly, things as you start to add more groups, axial conformations become less perfect. So you can see that these two methyl groups that are axial to each other are not perfectly axial, and this is no longer a perfect chair. The chair will try to distort itself to avoid steric problems. Yeah.
So obviously equatorial is more stable than axial, but when it comes to the A value, is that for an equatorial group or for an axial group, or just a combination?
That's difference in free energy between axial versus equatorial. So if you set the equatorial conformation to 0, the axial is this much higher than that. Yep. And for the most part, in OChem, we care about energy differences. So on your computational assignment, there were times where I asked you to talk about the difference between two different conformations, and I said set the lowest energy one equal to 0. That's just because all we care about is the difference. Your computations calculate, I think those numbers represent how much lower in energy your molecule is than all of the atoms and all of the electrons separated and at infinite distance. And generally that's not how we make molecules, so that's not relevant. But the differences are. Some people have done some creative things with cyclohexane rings to measure strengths of non-covalent interactions. As an example, Eric Anslin, who is one of the authors of your text, published this in JAX in the 90s. And he was interested in the strength of hydrogen bonds. And so he took this substituted cyclohexane. Oops, sorry. The two groups are trans, the two OHs are trans, and he measured the equilibrium constant, or the change in free energy, as you go from a conformation where the isopropyl is equatorial to where it is axial. The interesting thing is, though, that when the isopropyl group is axial, those trans hydroxyls stay trans, but they become equatorial, and that brings them close enough to each other to potentially hydrogen bond. And so he measured this change in folding free energy, and then he used the A values up here to account for how much better it is to have isopropyl equatorial versus axial, how much better it is to have OHs equatorial versus axial. And he assumed that the difference in energy between these two would be related to the A value of the isopropyl group. So it's like, that's like 2.2. And that's uphill in free energy because you're going from equatorial to axial. And then he subtracted 2 times the A value of the OH group because you were going from axial to equatorial. And he reasoned that whatever was left might be the energy of a hydrogen bond. So by measuring this free energy or equilibrium constant and then subtracting this term for the change in A values, he could come up with how much the hydrogen bond was worth. So kind of a cute little study. Of course, hydrogen bond strength varies dramatically as a function of context. If your solvent is water, it's different than if it's a non-polar solvent. And that's true in the protein folding world as well. Generally, you're thinking of anywhere between 1 to 10 kilocalories per mole. All right. Since this is a physical organic chemistry course, I just have to pay temporary lip service to all of the crazy ring structures that people have made in a desire to understand ring strain. There are a few important principles that are maybe interesting. One is that as you've looked, we have some type of rings where the strain is pretty high. And then we have other types of rings where the strain is pretty low. And maybe we have some other intermediate strain as we go from 9 to 10 to 11. So we've already talked about why ring strain is pretty high in the 3 to 4 region. We've talked about why it gets relieved when you go to 6. Why does it start going up again when you increase the number of atoms? And the reason for that is that there's no nice chair conformation that allows you to have perfect bond angles and no eclipsed interactions. In particular, here is a low energy conformation of cyclodecane, and as you look at it and show the space filling model, you're actually bringing CHs from across the ring and bumping into each other. And that's part of the reason why the ring strain goes up, is simply by trying to keep all the bond angles reasonable, you end up with CHs pointing at each other. This is much worse than, say, the axial protons on a cyclohexane ring, because those are parallel to each other and these are pointing to each other. Would I expect you to predict that this is the case? No. But realize if you're going to be making rings, if you're going to do macrocyclization in your research, you might expect it to be straightforward for rings of this size, sort of from 5 to 8, but you might expect to have some trouble in the sort of 9 to 11 region. And then beyond that, the ring strain doesn't go up a lot, but you've still got the problem of taking two groups that are far away from each other and bringing them together. So making rings is a famous and important part of OChem. I'm actually going to talk a little bit about that in my research talk tomorrow, but be aware of those kinds of things. And when someone makes a really, really large ring successfully, that's impressive. When someone has a reaction that really works to make a ring where there's a lot of strain, that's impressive too. So, because many fields in chemistry were once dominated by probably men who were trying to impress each other, we have a bunch of molecules here that have increasing levels of strain. And the numbers are shown here. This is strain energy relative to non-strained analog compounds. So
these have all been synthesized?
Have all been synthesized, but I don't think many of them are that stable. And so maybe some of these are just estimates. Let's see, what's worth talking about? The trans decalin. This is a 10 carbon system, 2 fused cyclohexane rings, almost no ring strain. I don't know what negative ring strain means. Maybe this means it's even happier than it would otherwise be linear. You go with cis, and that's strained. The reason for that is the cis fused ring system always has to have one axial and one equatorial, whereas the transfused ring system, you can have both ring substituents equatorial. Some of the bicyclic ring systems have interesting amounts of strain. So let's see. Here's a 5-membered ring, and here's 2 5-membered rings fused together, and it's not that much more unstable. One of the interesting things to look at, though, is what happens when you try to bring a double bond near that bridgehead carbon. We won't talk very much about this, but if you ever get into physical organic chemistry, there was a question as to whether there could really be a p orbital there overlapping with this carbon to make a double bond. Let's see. Some of the more exotic ones are cubane and tetrahedrane. And then, let's see, which ones most offend our sensibilities? Maybe this benzene ring with the cyclopropane ring attached to it. That just seems like that bond angle wants to be 120, and now it's forced to be something less than that. Here's an interesting one. You may have learned that you can't have trans double bonds in 6-membered rings. It just doesn't work out. You can't close the ring. The smallest size ring that allows you to have a trans double bond is the octane, cyclooctane. So you can have trans cyclooctane. Here's what it looks like, and it has to twist so that the double bond is sort of lying on its side, and one proton is up and one proton's up and the other is down. So we're looking at the ring, we're looking on the edge, and here's a proton coming towards us, here's one going back in the page. The bond angles are not perfect for a double bond, so you might expect that to be a little bit more reactive than a double bond is. You can see this is not perfectly flat, it's sort of pyramidalized, but you can force it and make it work. The idea of incorporating bonds into rings that would make the ring particularly strained has become really useful in organic chemistry. So years ago, there was a study about a cycloaddition that was called the Huygens cycloaddition. And this was a reaction where you took an azide and an alkyne, and I think if you cooked them and let them sort of stare at each other, the reaction really wasn't that efficient, but you could eventually maybe get the following heterocycle, which is called a triazole. Okay. wasn't that useful back then. But more recently, in the mid 90s, I think, and early 2000s, Barry Sharpless and others found that if you added a copper-1 catalyst, that reaction went really well at room temperature in various solvents. And the nice thing about it is that if you're dealing with biological molecules, they don't naturally have a lot of azides or alkynes, and so you can do some interesting chemistry in the presence of unprotected biological molecules. That will take, so the copper catalyst greatly accelerates the cycloaddition. This is often called the copper catalyzed, this is not like it would make it easier to say, azide alkyne cycloaddition. People often say it's click chemistry. That's a word in chemistry for reactions that are efficient and proceed without interference from other biological functional groups. We call them bio-orthogonal reactions. Sometimes people call this the click reaction. Click chemistry more properly applies to a bunch of reactions that satisfy these criteria of being efficient, easy, and orthogonal to other biological functional groups. Sometimes you'll see people abbreviate this as CUAAC, AC, or something. When I'm writing, I often just abbreviate like that because this is often hard to do. So a lot of people have used this reaction for a lot of different purposes. But one of the things that people have wanted to do is to use this to, in the presence of biological systems. What if you could somehow get a protein to incorporate an azide? And it turns out there are ways to do that. Could you then specifically label a particular protein with some fluorophore or some other useful functional group just by making that group attached to an alkyne, and then you do the azide alkyne cycloaddition. You got the triazole linkage, you've clicked the thing you want onto the protein just at that spot. You can make proteins with new properties. The challenge is that copper-1, there's sort of two challenges. Copper-1 wants to oxidize to copper-2 in air, so you have to do something to keep it reduced. Second, copper tends to be toxic to biology in large amounts. So the challenge was, how do we get this reaction to go faster if you don't use the copper catalyst? Because then you're sort of back to the drawing board of the azide alkyne cycloaddition that doesn't work well. Enter Carolyn Bertozzi, based on work by Wittig, made this cyclooctane ring. Now that's an alkyne in an 8-membered ring. That should be highly strained because the bond angles want to be linear, but they're constrained to be something different from that. We don't have a representation here of what that ring conformation actually is. But when you bring this strained ring into the presence of an azide, the relief of that ring strain, turning it from turning these carbons from sp hybridized to sp2 with a sort of cis double bond, that strain relief is enough to drive the reaction, and it actually works quite well. So this is called the strain promoted or copper-free azide alkyne cycloaddition. And this isn't the only cyclooctane that's used. There are others as well. But Bertozzi has done this a lot. She's labeled living cells with azides on their surface. She in the classic and maybe most famous experiment, she fed cells carbohydrates that had azido groups on them, and the cells incorporated those carbohydrates into their surface proteins, and then she threw a cyclooctane linked to something else, perhaps a fluorophore, at the molecules and labeled the surface, and the cells were still alive. And so there's a lot of interesting things you can do with that technology, but that's based on ring strain. Okay, anything else we need to talk about there?
The stuff we wrote there, is it shapeless or sharpless?
Sharpless, yeah. That's Professor K. Barry Sharpless at the Scripps Research Institute. He won a Nobel Prize, I think, in the early 2000s for the asymmetric epoxidation reaction. And there are people who have speculated since then that it might be worth a Nobel Prize. This other reaction might also be worth a Nobel Prize.
Okay, so he was the one.
He was the one that said, "Hey, let's try copper." Yeah. Let's see. And these issues are important in the Savage group. So Paul Savage's group has one of their projects in which they make carbohydrate antigens for various bacteria and viruses. Go ahead.
You can finish for a second. I wish not to. So,
Oh.
how do you choose copper? Like, they just random one day
They
say,
just-
hey,
yeah.
I dump copper in my
Oh,
it's like,
why copper?
yeah. Like,
I don't know. I suspect there was a rationale, and it probably has to do with copper's other chemistry and whether it was similar or not.
okay.
There's two ways you do research, right? You do research where you think you have a hypothesis and you try it and it either works or doesn't, and then you adjust. And there's also research where you throw the kitchen sink at a problem and just try a bunch of things and then you see what works.
Okay.
A lot of asymmetric, like make enantioselective reactions, in many cases what they do is they have a reaction that works, and then they're like, how do we make it enantioselective? Well, let's try some chiral ligands for this metal. Well, this one doesn't work. How about this one? Well, how many can we buy? Or how many can we make? And let's try them all. So it depends, and I don't know what the story is. But the student or the postdoc who was in Sharpless's lab when this was discovered is named M.G. Finn, and he's now a very famous chemist, and he collaborates with the Savage Lab. The Savage Lab makes these carbohydrate antigens that bacteria make, and they conjugate them to azides or alkynes, and then they send those to M.G. Finn's lab. He has these virus-like particles, which are these sort of nanoparticle-sized things made of proteins, into which he has incorporated azides or alkynes. So they conjugate their carbohydrates onto the surface of this virus-like particle, and then they use that as the basis for a vaccine. And the idea is, could you vaccinate people against various bacterial infections? Could you vaccinate them against viruses that have been difficult? And they've had quite a lot of success there. So this reaction is really quite important. It doesn't work in our lab's hands as well. I think anybody that's tried it will tell you it doesn't work quite as well as the hype says. If you're going to do the copper catalyzed azide alkyne cycloaddition, its efficiency depends a lot on the concentration of copper and alkyne and azide. It depends a lot on the solution. There are times when we've been able to get it to work and times where we haven't, and it can be something of a challenge. I've never done the strain promoted one, so I don't know how easy that is to do. But if you ever decide you want to do that, come talk to somebody in the Savage Lab or one of my grad students, because we can probably save you some time messing around and not getting stuff to work. Okay, let's see. So the idea of strain and dihedral angles is really important in peptide and protein folding. And a lot of these principles of physical organic chemistry really influenced over the past 20 years the chemical biology of peptides and proteins. So even though this isn't a biochem class, because it's my class, I can sometimes talk about things that I'm interested in. So this isn't in your text, but I feel like it's useful to know. So here is a peptide. A peptide is an oligomer of amino acids. An amino acid is a molecule that has a carboxylic acid and an amino group. These amino acids are linked together via amide bonds. I've labeled the individual amino acid subunits. You have a carbonyl carbon, often labeled C. you have a carbon that is alpha or adjacent to that carbonyl carbon, call that the alpha carbon. Branching off the alpha carbon, you have a side chain, and in most, in all of our proteinogenic amino acids, the ones that we make proteins of all have this stereochemistry. For most of the amino acids, it's S. But anyway, with the R group down when you've got this orientation. And then you've got the amino group. And the amino group of one amino acid is tied up in an amide bond with the other amino acid. And so you can have chains that are hundreds of amino acids long. Without worrying about what the side chains are, though, there are 3 different bonds to think about that you could potentially rotate around for each of these amino acids. And rotation around these bonds is important because that's how a chain of amino acids adopts a structure like a helix or a sheet, and those are important for protein folding. So for whatever reason, we call the dihedral angle about this bond between carbonyl carbon and nitrogen for the next amino acid, omega. That's my attempt at the lowercase Greek letter omega, so sorry. The next bond between nitrogen and alpha carbon, that dihedral angle or rotation around that bond is called phi. And then the next bond between alpha carbon and carbonyl carbon, we call that psi, as though we didn't have enough uses for psi already, but whatever. Now, notice that the omega angle is between groups that ought to be sp2 hybridized. We think of amides as being planar. We think of the nitrogen here being tied up in resonance with the carbonyl carbon, so we expect both the nitrogen and the oxygen to be planar. And so there are really only 2 different dihedral angles that you could adopt there. You could adopt one where the OH is anti to the, where the oxygen of the carbonyl carbon is anti to the amide proton, or you could adopt one where it's eclipsed. So here we have our 3 amino acids, and we're going to be talking about the dihedral angles that might allow these amino acids to be part of an alpha helix. I just happen to have highlighted 3 here. Sometimes in talking about amino acids, we'll start with an arbitrary position, which we will call I, and then I+1 is the next one, I+2 is the next one. Generally, amino acids have a directionality, that is, we read them from the amino side to the carboxylate side. So that's why this is I+1 and I+2 instead of I-1 and I-2. Okay, so that dihedral angle omega, if we're looking down, zooming in on this portion of our helix, and we're going to look down the bond between carbonyl carbon and amide nitrogen. This is the I position residue, this is I+1. And if we look down that bond, and these are snapshots of the protein generated in a program called PyMol, we can't see the NH bond because it's actually directly behind our bond between alpha carbon and carbonyl carbon. In a Newman projection, we might represent it this way. The alpha carbon of the orange amino acid is anti to the alpha carbon of the purple amino acid. So that's a trans orientation. Now at this stage you might be saying, well, hold on, that looks like an eclipsed conformation. Isn't that a problem? And you're right, it is an eclipsed conformation, but you're paying for it by the fact that you've got resonance here and double bond character there. There's simply no other option. So in most proteins, this omega angle is 180 degrees. There are some times when it's 0, but those situations tend to be difficult. Questions so far? Sort of see how we're zooming in on these different amino acids. Okay, now we're going to look at phi, and I think we're going to look down the angle between purple nitrogen and alpha carbon. So this is the phi dihedral angle. And I will post these notes, so if you're not able to get it down clearly, you're not going to draw this. So you'll have access to these things. the dihedral angle phi is if we look down this bond between amide nitrogen and alpha carbon. And then we're going to look specifically, excuse me, at the angle between the two bonds that I've sort of labeled in gray. So on the nitrogen in the front, we're going to look at the bond, we're going to focus on the bond between nitrogen and carbonyl carbon. For the alpha carbon in the back, we're going to focus on the bond between that alpha carbon and the carbonyl carbon, because the phi angle should describe the behavior of the peptide backbone, and these are the bonds that are involved in the peptide backbone. So if we look down that bond, and here's the view in the PyMol program. Here is our nitrogen in the front. You can't see the alpha carbon in the back. In the nitrogen in the front, it's bonded to this carbonyl carbon here. And then the alpha carbon in the back is bonded to a hydrogen, a side chain, and then the carbonyl carbon, the purple carbonyl carbon. So we're going to measure the angle between those two bonds, the dihedral angle there. And within an alpha helix, the phi angle tends to be around minus 57 degrees. Why is it minus? I don't know, because the bond in the back is on the left-hand side of the bond in the front. I don't know why it's that way. Go ahead.
Did those not clash at all to groups of the carbonyls?
Do these two not clash?
Yeah, do they ever?
Yeah, so you would expect there to be, I mean, this is a gauche interaction. The question is it better or worse than the alternatives? You can imagine if you started twisting around this bond and bringing that carbonyl carbon down this way, eventually you're going to get close to the side chain. And these side chains are often quite big, and so you're right, you know, what angle should you adopt? And there are many of them that can be adopted here. I guess the interesting question to ask is, why does it do this?
Yeah.
And that's actually kind of complicated. Because that's the same thing really as asking what makes an alpha helix form anyway. And the short answer to that is a lot of things. One is hydrogen bonds from one level of the helix to another, but usually that's not enough. Usually you have to have some burial of hydrophobic surface area to drive the process forward. We'll talk about that in chapter 3 more. All right. And there are some amino acids that actually struggle to adopt this phi angle, and so are not great in alpha helices. Okay, so the psi angle then is going to be, scrolling back up, this angle between alpha carbon and carbonyl carbon. So let's look at that. We're still zoomed in on our alpha helix. Nope, that was phi. There we are. So alpha carbon on the purple amino acid to carbonyl carbon. We're going to look down that bond. We're going to be focusing on the bond between alpha carbon and amide nitrogen here in the front, and then in the back in the bond between carbonyl carbon and amide nitrogen. And if you look down that bond, what you can see is that you've got another sort of gauche interaction. The bond between alpha carbon and amide nitrogen here, and then in the back you can't see the carbonyl carbon, but the bond between that carbonyl carbon and the next nitrogen is there, and the angle between those two is psi. You can see that that angle is a little tighter than the phi angle previously. It's still negative because the bond in the back is sort of on the counterclockwise side of the bond in the front. In alpha helices, the psi angle tends to be around 47, minus 47. Okay. So people that are interested in understanding protein structure often measure these dihedral angles for each amino acid in the structure, and then they plot them in an interesting way. I told you that the omega angle generally is 180 or 0, so people aren't that interested in the omega angle. But phi and psi can adopt a lot of different values. And so what people will do is they'll have a two-dimensional plot. On the x-axis, they'll have phi dihedral angles, And on the y-axis, they'll have psi dihedral angles. And these can vary anywhere between 180 and minus 180 for phi, and same thing for psi. Of course, plus 180 and minus 180 end up being the same thing. But so for each of our amino acids, you could go in this segment of an alpha helix, you could go in and measure the phi and the psi angles. We did that for the purple amino acid. I've done it previously for the orange amino acid and the green amino acid, and these are the angles you get. Most of the phi angles are in the mid to upper 50s. Most of the psi angles are in the mid to upper 40s. And if you plot phi versus psi, you can see that residues with amino acids within an alpha helix all cluster in this section of the plot. So if you wanted to know how much of a protein was alpha helical, you could almost just measure all of the phi-psi angles and plot them, and the ones that ended up here would have a high likelihood of being in the alpha helical conformation. What else?
Alpha helixes always show up around that.
Yes, alpha helices always show up here. Exception. It won't make sense from what we've talked about, but this alpha helix is a right-handed alpha helix. How do you know it's right-handed? You don't have to. If you want to know real quick, you take your thumb and you point it towards the carbonyl, you point it towards the C-terminus of the helix, and if your fingers wrap around in the direction that the helix wraps, then that's a right-handed helix. Proteins made of L amino acids, which ours are, tend to form right-handed alpha helical conformations. As you might expect, though, don't you remember when we were doing if you're in your computational assignment, we were doing stuff with pentane, and we discovered that gauche plus was exactly the same as gauche minus. Same thing here. There's another spot sort of in this region at plus 57, plus 47, and this would be a left-handed alpha helix. And you can make those if you make your peptide out of D amino acids. And there are some side chains that are actually okay adopting those structures. Most of the L amino acids don't like adopting this particular set of dihedral angles because there's a lot of steric clash. So, oh, I said that here. Oh well. So here's a diagram that illustrates how you can convince yourself that the helix is right-handed. Here is a more complete representation of the Ramachandran plot. Phi on this axis, psi here. The dots represent individual observations for amino acids in the protein data bank. I can't remember how many are represented by here. You can see that most of them have negative values for phi, though values for psi can be all over the place, negative or positive. Amino acids that are in this region tend to be in helices. Amino acids in this region tend to be in sheets. Amino acids in this region tend to be in polyproline helices. And this is the opposite. This is where left-handed alpha helical residues might show up. And there's much fewer of those than there are here, and that's because of the difference in stereochemistry. Interestingly, if we snapped our fingers and the world was made of D amino acids, what we would see would just be the reflection of this plot through the origin. Okay, lastly, copy all this down, right? People have done studies about each different amino acid and what its preferred dihedral angles are, and there's actually some interesting differences. And people that are interested in designing peptides and proteins with specific structures, often you want to tailor your choice of amino acid to match the structural context. So for example, these are heat maps where red represents high population, high number of observations. Phi is still x-axis, psi is still y-axis. These are from a paper in a crystallography journal that I should have cited here, but I didn't. But if you want to know more about it, I can get you the reference. Alanine is comfortable in alpha helices, like a lot. Another way of saying that is the amino acid alanine. That's where the side chain is just a methyl group, has a high helix propensity. It's also okay in beta sheets and in polyproline helices. There are some that are kind of weird. You can do this for all the amino acids. Aspartate, this is an amino acid where here's the alpha carbon, and then you have a carboxylic acid here. These are actually strangely okay, adopting the left-handed alpha helix conformation. They're fine in regular alpha helices, not so great with beta, in beta sheets, but they're actually pretty good in certain kinds of beta turns. Glycine is another interesting one. What's going on there? Well, glycine doesn't have a stereocenter at the alpha carbon. So you wouldn't expect glycine to have a preference for left-handed versus right-handed alpha helices, except for the fact that glycines occur in proteins that have lots of L-amino acids. But glycine can adopt dihedral angles with left-handed alpha helical or right-handed alpha helical structures. Anyway, there's more we could say, but if in your grad studies you hear things about the propensity of each amino acid to exist in a helix versus a sheet, that's coming from this kind of analysis and the kind of dihedral angles that are preferred. Why are they different? Well, the difference between each amino acid is in the identity of this R group. And so you can imagine, depending on the size of that R group, what its functional groups are, you might imagine that you could be biased to have this group further away from the R group than from other groups. And that's one of the ways in which side chain structure influences protein, side chain identity influences protein folding and structure. Okay, so that's enough of me nerding out. So naturally you want to know, how much of this do we have to remember? Well, probably if I pasted it in so I wouldn't have to write it down fast, it's not something you need to memorize. I do want you to know the definition of phi and psi and omega angles. And because it frankly took me a long time to figure that out. I remember sitting in a biochemistry class here in W140, and they were, when I was an undergrad here, and they were talking about phi and psi angles, and I was like, why is this important? I just don't get it. And it took me a while to figure it out. It turns out it became very important for my grad study. So, lesson: just because you think something is silly or boring doesn't mean it won't be important to you in your future. Another story about that is that I took biophysical chemistry here, and we learned about some weird technique called circular dichroism, and I'm like, this is so esoteric and boring. Who would ever do this? And now it's basically all I do. We use it to assess whether a protein is in a helical conformation or a sheet conformation. There's lots of other great things you can do with it, but sometimes first impressions aren't necessarily accurate in terms of how the rest of your life is going to go. Okay, any other questions you want to ask about protein folding? Should you memorize that alpha helices have phi psi angles of -57 and -47? I suppose you could, but if you did, that would defeat the purpose of me asking about it. Generally, I don't ask questions about that ask whether or not you can memorize something. But be aware of it and be able to reason your way through some of these things. I'll see if I can find an example question that I've asked in the past on this and maybe show it to you next time. Okay, what else? So we've dealt mostly with how sterics and strain influence the structure of organic molecules. We now want to talk about how electronic factors can influence molecules. So we're going to start And I guess we could call this, there's a lot of electronic factors, some of which I think are straightforward to understand. We may not talk a lot about aromaticity because I think you guys already know about it. And I don't know that there's that much we need to say that's extra. So don't forget that. Aromaticity is still important, but we may not spend a lot of time on it. Stereoelectronic effects. These are effects that happen because of the particular orientation of groups relative to each other that introduce some kind of interaction that can change the stability of a molecule. So the first one is called the Gauche effect. All right, so here is 1,2-difluoroethane. And I've drawn it as though it would be in the anti-conformation. What reason would I have to believe that the anti-conformation is, when I have the fluoro groups anti to each other, what reason do I have to believe that that might be better than, say, having the fluoro groups gauche to each other? For butane anyway, why did you say anti was better than gauche? Sorry? Anti has lower energy, good, and why is that? More stable because sterics. Yeah, because of steric hindrance, it minimizes the steric hindrance between the two methyl groups. Now, fluoro groups are actually quite a bit smaller than methyl groups, but they're still a little bigger than hydrogen. So you might expect that the anti-conformation might be better than the gauche conformation because the anti-conformation minimizes steric hindrance. However, dun dun dun, for this 1,2-difluoroethane, the gauche conformation is actually more stable. So there's a fun rule of thumb in organic chemistry that people say if it's not sterics, it's got to be electronics. So if you can't explain an effect based on the size of a group, you want to start thinking about what might be happening with the electrons. Okay, so let's think about bonding in this molecule. And in doing so, we're going to think about a hybrid between valence bond theory and molecular orbital theory. That is, we're still going to think about bonds as being localized between two atoms, even though we know we don't have to. But we'll keep in mind the idea of there being both bonding and antibonding orbitals. Okay? So, associated with each of these bonds is a bonding orbital and an antibonding orbital. So let's talk about the energies of CH bonds versus CF bonds and their antibonding orbitals. So here we'll have carbon, and let's maybe put carbon in the middle. We'll have hydrogen over here and fluorine here. So let's just say that the orbital that contributes to a sigma bond on carbon is an sp3 orbital. And an orbital that contributes to the sigma bond on hydrogen is a 1s orbital. The orbital that contributes to a bond on fluorine should be one of the two p orbitals. Now, here's the trick. Where should that fluorine p orbital be in relation to the carbon sp3? Probably lower because of fluorine's more electronegative. Now, if you're worried about the fact that this sp3 orbital has some 2s character in it and won't that pull it down, yes, this isn't going to be as low, this isn't going to be as high in energy as a 2p orbital on carbon, but that's not enough to compensate for the fact that fluorine's high electronegativity means, and I really don't care actually about the relative relationship between the 1s on hydrogen with the fluorine, don't infer anything from there. Well, that orbital is going to be quite, I actually do mean to infer something there. Because of fluorine's electronegativity, the 2p orbital on fluorine is quite a bit lower in energy than either the carbon or the hydrogen orbital. So when we make a sigma bond, oh, and we're done. We're out of time. So in the meantime, think about where the sigma bond and the sigma star antibonding orbitals are going to be for the carbon-fluorine bond versus the carbon-hydrogen bond. We'll pick that up next time.